Have you ever noticed how clocks just keep going? Whether you're paying attention or not, the second hand moves. Day turns into night. You get older, planets spin, stars shine, galaxies drift apart. It all feels automatic, like the universe is following some unspoken rhythm, something built in, something permanent. But here's the thing. Just because something seems constant now doesn't mean it always will be. Time, motion, energy, they all feel infinite. But they're not. They're temporary. Like everything else in nature, they change. They decay. They end. And if we zoom far enough into the future, not decades, not centuries, but trillions upon trillions of years, things stop making sense. Not in a poetic way, literally. Physics starts acting strange. And we're not talking about science fiction or some random fringe theory. We're talking about where mainstream physics leads us when we ask one simple question. How does the universe end? Turns out, the end of everything isn't just a quiet fade into darkness. It's a slow, strange transformation. A place where familiar rules break down. Where reality becomes cold, quiet, and deeply weird. Not because we invented new physics, but because we kept following the old ones all the way to their final conclusions. So, let's go there. Not to the Big Bang, not to the present day, but to the end. The far future. A time when the stars are gone, the galaxies have disappeared, and even the atoms themselves have nothing left to say. Right now, we live in a golden age of light. Everywhere you look in the night sky, you're seeing stars in their prime, burning hydrogen, fusing elements, lighting up galaxies like cosmic street lamps. But that glow, that's not eternal. It's borrowed time. Stars are not permanent. They're engines. Engines with fuel tanks. And like every engine, they eventually run dry. Some go out with a bang, leaving behind neutron stars or black holes. Others die more quietly. A star like our sun will swell up into a red giant, shed its outer layers, and collapse into a white dwarf. This fate for stars of different masses was clarified by an Indian-American astrophysicist, Subrahmanyan Chandrasekhar, who in the 1930s calculated that stars below a critical mass, now called the Chandrasekhar limit, become white dwarfs, while heavier ones collapse into neutron stars or black holes after catastrophic explosions. The stars will glow for billions of years more, slowly cooling in the dark, until one day they will no longer give off any light at all. That's the first act of the universe's long goodbye. But it's not just one star, it's all of them. Across trillions of galaxies, the birth rate of stars is slowing. The universe used to be wild with creation, new stars forming constantly in giant gas clouds, but that gas is running out. The material that makes new stars is getting used up, and without fresh stars, the lights begin to dim. We're talking about a future so far ahead that the human brain can't really picture it. 10 trillion years, 100 trillion, maybe more. It doesn't feel like anything because there's nothing happening on a human scale anymore. But slowly, inevitably, the galaxies stop glowing. One by one, they fade out like dying embers. And what's left behind? A quiet universe full of leftovers. You'll still find white dwarfs, neutron stars, and the occasional black hole wandering the darkness. Some may still carry orbiting planets, frozen, forgotten worlds spinning silently around the remains of suns that haven't shone in 100 trillion years. That's not poetic exaggeration. That's just astrophysics stretched to its natural limit. And here's the thing. None of this requires anything new. No mysterious forces. No quantum magic. Just ordinary physics playing out to its final pages. Fusion stops. Heat leaks away. Motion slows down. Systems decay. At some point in the deep, deep future, the last red dwarf, the smallest, slowest burning star, will finally flicker out. It'll be the last point of warmth in the entire observable universe. And when that light goes out, there will never be another. That's the moment the curtain falls on starlight. The cosmic theater closes for good. No more light, no more warmth. Just the remains of a universe that used to shine. But don't be fooled. Just because it's dark doesn't mean it's over. The real weirdness? That's still ahead. Because now we're in a universe with almost no energy, no activity, and no creation. Now we've entered the degenerate era. This era underscores the impermanence of the universe's current vibrancy. This phase, while bleak, is a natural consequence of stellar evolution, as mapped by scientists like Hans Bethe and Chandrasekhar. And it sets the stage for a time where matter starts losing its meaning, and only the heavyweights remain, and the heaviest of them all? The black holes. Once the stars are gone, the universe starts to feel empty. But it's not. Not yet. Even after the last light fades, something still holds everything together. Not heat, not fusion, not radiation, but gravity. See, while most things in the universe burn out or fall apart, black holes don't. At least not at first. They're built different. The densest objects we know. No light escapes them. No information escapes them. They're not just leftovers from massive stars. They're the long-term survivors of every galactic collision, every supernova, every spiral dance of matter that ever spiraled too close to the edge. In this far-flung future, galaxies are no longer glowing disks. They're dark, quiet graves. And inside those graves? Black holes, lurking like sleeping giants scattered across the cosmos. This strange epoch is the black hole era. Over unimaginable timescales, these black holes start moving, not fast, not violent, just the slow ballet of gravity. They drift. Some collide. Others form larger systems. The few remaining pieces of matter, rogue planets, brown dwarfs, maybe even the last neutron stars, are slowly consumed. This is a gradual process where black holes accrete matter that ventures too close. Gravity pulls these objects or particles into the black hole's influence. But even that doesn't last forever. After enough time, even collisions become rare. Space has stretched too far. Everything is too spread out. The universe is not just dark now, it's silent. Black holes sit in the middle of that silence. They don't glow, they don't move much, they just are. But here's the twist. Black holes aren't eternal either. They evaporate. It sounds strange. It is strange, because black holes are known for swallowing things, not disappearing. But thanks to Stephen Hawking, we know that black holes actually lose mass over time. Not quickly, not in any way you'd notice in our lifetime, but slowly through something called Hawking radiation. The idea is this. The vacuum of space isn't empty. Quantum mechanics says it's always fizzing with temporary particles popping in and out of existence. Usually they annihilate each other and vanish. But near the edge of a black hole, right on the event horizon, virtual particles can get split up. One falls in, the other escapes. That escaping particle, it steals a bit of the black hole's energy. Over time, that energy loss adds up. It's tiny, laughably small. A supermassive black hole would take 100 years to fully evaporate. That's a 1 followed by 100 zeros, a number so big it makes the current age of the universe, just 13.8 billion years, feel like the blink of an eye. But the universe is patient. Eventually, over that timescale, even the biggest black holes fade. They lose energy, bit by bit, until there's nothing left but a puff of radiation. No bang, no collapse. Just a soft goodbye. And after that, there are no more engines. No more light. No more gravitational beasts waiting in the dark. Nothing remains but a near-perfect vacuum. Just a scattering of subatomic particles, radiation stretched so thin it barely counts, and an empty stage where all the actors have left. We are now in a universe where even gravity, the last force that held anything together, has run out of things to hold. It's hard to imagine because we've never seen true nothingness. Even empty rooms still have air. Even the vacuum of space still has starlight. But in this distant epoch, there's no light, no stars, no matter, no black holes, and almost no heat. The universe hasn't exploded. It hasn't collapsed. It's simply decayed. But somehow, this isn't the end of the weirdness. Because now, without stars or black holes or atoms to distract us, the only thing left ticking is the quantum world. By the time the last black hole evaporates, the universe has already lost almost everything we recognize. There are no stars, no galaxies, no light, no explosions, no structure. Only a thin, dark expanse that keeps stretching wider and colder. But strangely, the universe isn't entirely empty yet. Not completely. What remains are the leftovers of leftovers. White dwarfs, those dense, burnt-out cores of stars, still exist, although they're not glowing anymore. After trillions of years, they've cooled so much they're just cold black dwarfs now. They don't emit light. They just sit there, dead and dense, drifting in the dark. Neutron stars, those collapsed cores of massive stars, are still hanging around too. And so are the rogue planets, the ones that were ejected from their systems long ago. There might even be some stray particles, or lone molecules floating across the void. It's not much, but technically, it's still matter. But here's the problem. All this stuff is useless. Energy in the universe flows from hot to cold. That's how work gets done. That's why stars shine, why engines run, why life exists. But now everything's cold. There's no gradient left, no difference to drive anything, no heat to move things along. And so, even though particles still exist, nothing's really happening. This is entropy at its peak. The universe isn't dead in the explosive, dramatic way we usually imagine. It's just quiet, still, like a clock that hasn't been smashed, just wound down so far it can't tick anymore. It's a strange kind of existence. Matter is technically there, but it's meaningless now. There are no stars to orbit, no galaxies to fall into, no black holes to devour it. Space has stretched so much that everything is isolated. Every object is alone, too far from anything else to ever interact. The universe becomes a museum of cosmic fossils. A black dwarf here, a neutron star there, a lonely proton still drifting from a galaxy that stopped existing eons ago, all frozen, all motionless. Not because something broke, but because everything worked exactly as it was supposed to. For too long, and this era could last forever. Unless protons themselves decay. That's the big question. According to the standard model of physics, protons might be stable. They might last for eternity. But some theories, especially those that try to unify the forces of nature, suggest that protons can decay very, very slowly. Two leading figures who made foundational contributions to the development of grand unified theories and the concept of proton decay are Howard Georgi and Sheldon Glashow. The predicted lifetime is extremely long. We're talking decay times of at least 10 to the power of 34 years. That's a number that makes even black hole lifespans look short. But if it's true, then even the atoms of this degenerate era aren't safe. They'll eventually crumble into radiation. And when that happens, the last solid particles in the universe will vanish. No more matter. No more atoms. Nothing but radiation, fading deeper into the background, stretched thinner by expansion until it becomes unmeasurable. It sounds surreal, but this is all still just basic physics. No new rules, no magic. Just gravity, thermodynamics, particle physics, and time doing their thing, to the bitter end. And the deeper we go, the weirder it gets. Because once even the protons are gone, the universe doesn't shut off. It doesn't go black. It stays black. And black isn't the same as empty. Because even in the absence of matter, the vacuum isn't really empty. There are still fields, there's still space, there's still quantum mechanics, and that's where things start bending again. Because now, with nothing left to move or decay or interact, the universe becomes a blank canvas for the strangest possibilities physics has to offer. By now, the universe has lost almost everything it once had. No light, no heat, no stars or black holes. Just a few ancient remnants scattered through expanding space. But even those leftovers aren't safe. Because if one specific process turns out to be true, proton decay, then even the most stubborn building blocks of matter will eventually break down. Let's talk about protons for a second. Every atom is built on protons. They're inside the nuclei of atoms, paired up with neutrons, surrounded by electrons. But compared to electrons, protons are much bigger and heavier. They're the things that make matter matter. Without them, atoms wouldn't exist. And for most of modern physics, protons were thought to be stable, eternal. After all, we've never seen one decay. But grand unified theories, the kinds of theories that try to combine the strong, weak, and electromagnetic forces, predict that protons don't last forever. They decay. Very slowly, yes. Incredibly slowly. But still, decay. How slowly? Well, according to some estimates, a proton might last 10 to the power of 34 years before it decays. That's longer than the current age of the universe by roughly 750 billion trillion. But remember, time doesn't care how long something takes. The universe is in no rush, it'll wait. And so, if proton decay is real, then even the cold, quiet remnants of the degenerate era, the black dwarfs, neutron stars, rogue planets, and floating matter, will eventually disintegrate. The protons inside them will spontaneously decay into lighter particles, mostly positrons and photons. Over time, everything solid will disappear. Not in a fire or explosion, but quietly through decay. There's no energy left to hold anything together. No structures, no systems, just a thin, invisible soup of fundamental particles and radiation drifting endlessly apart. Even the neutron stars, those dense relics that seemed untouchable, might crumble. Over long enough timescales, even the particles inside them may not hold up. And once that happens, the universe enters a new phase. Post-proton decay radiation. But don't let the name fool you. This isn't a bright or fiery time. It's not like the early universe, full of light and plasma. It's the exact opposite. This is radiation stretched across the thinnest vacuum imaginable. A few particles per galaxy's worth of space, too spread out to interact, too cold to matter. These are photons and neutrinos left behind by all the decay. They move through space, but they don't do anything, they don't collide. They don't form anything new. They're just there, spreading thinner and thinner as the universe keeps expanding. It's a quiet kind of chaos, a sea of decay products drifting forever into the dark. And yet, even here, even now, the universe isn't entirely dead, because space itself still exists. And space is never truly empty. At this point, physics starts feeling more like philosophy. Because if there's nothing happening, is time still ticking? If everything that can happen has already happened, what's left? But before we get into the death of time, there's one more twist physics throws at us. Because even after the last particles decay and the last black hole fizzles out, quantum mechanics keeps whispering in the void. And in that whisper, something very strange might emerge. Even in a universe stripped of stars, stripped of black holes, stripped of matter, there's still something left. The vacuum. It sounds like nothing. But in physics, vacuum isn't truly empty. It's a kind of stage, an invisible energetic field that every particle sits on. Even when space seems silent and still, it's defined by the vacuum it rests in. And that vacuum may not be stable. Here's where it gets strange. Right now, our universe works because certain values are just right. The Higgs field, for example, it gives particles their mass. Without it, atoms wouldn't hold together, stars wouldn't form, chemistry wouldn't happen. The numbers line up in just the right way to allow a stable universe. But that stability might be an illusion. Theoretical physicists Gianfrancesco Giudice and John Ellis explored this unsettling possibility. After the discovery of the Higgs boson, they ran the numbers, and what they found was unnerving. According to their calculations, our vacuum state, the one we live in, might not be the lowest energy state possible. It might just be metastable. That means it works for now. But there's a deeper, more stable vacuum out there. One that the universe could, in theory, fall into. And how would that happen? Through vacuum decay. Vacuum decay is a theoretical process in which the universe's current vacuum state, which defines the fundamental properties of particles and forces, transitions to a lower energy vacuum state, potentially altering the laws of physics. A small region of space could spontaneously shift to the true vacuum state due to quantum fluctuations. This region, called a bubble of true vacuum, would then expand at nearly the speed of light, converting the surrounding metastable vacuum into the true vacuum. The laws of physics themselves get replaced. There's no warning, no time to react, no escape. It's not an explosion in the usual sense. There's no debris, no shockwave, no heat, just replacement. Everything you knew about particles, mass, charge, interaction, it all vanishes inside the new vacuum. What's left might be incompatible with atoms or even time. It could be a flat nothingness, or it could birth an entirely different set of physical laws. We don't know what would come next, but we're pretty sure we wouldn't be around through the transition. Now here's the part that really messes with our sense of time. Vacuum decay could happen at any moment, not in the far future, not in a dying universe. Even now, even here, even inside you. Quantum fluctuations don't ask for permission. The only reason we haven't seen it yet is pure probability. But in the far future, in a universe stretched thin, cold, and empty, there's a lot more space for those probabilities to play out. More room, more time, more chances. And since there's no energy cost for the vacuum decay bubble to expand through empty space, once it starts, it doesn't stop. One fluctuation, one bubble, one tick in the quantum dice roll, and the entire universe rewrites itself. All the physics we know, all the constants we rely on, all the particles we're made from, they could vanish, not through violence, but through irrelevance. Replaced by something more stable, more fundamental. It's like finding out the ground you've been standing on isn't solid, but ice. And beneath the ice is something deeper, older, and nothing like what you thought was real. Vacuum decay isn't just the end of stuff, it's the end of meaning. Because if the rules of physics can suddenly change, then nothing is truly permanent, not even the concept of permanence. It's worth mentioning that this isn't fringe speculation. Physicists have done the math. Based on the mass of the Higgs boson and the top quark, our universe sits uncomfortably close to that metastable line. We don't know for sure if it's stable or not. But if it's not, then vacuum decay isn't just possible. It's inevitable. And yet, the scariest part isn't the decay itself. It's the silence before it happens. Because now the universe is empty, cold, dark, waiting. And that's where quantum mechanics starts doing something even stranger. Not loud, not violent, but weird in a quiet, statistical way. Because even when there's nothing left, quantum mechanics doesn't stop. By this point in the universe's story, everything that could fade has faded. Every star has burned out. Every black hole has evaporated. Every atom has crumbled into radiation. Space is colder than we can imagine. Time is still ticking, but not much is happening anymore. And yet, there's still one thing that hasn't gone silent. Quantum mechanics. See, even when a system seems completely stable, even when there's no energy, no heat, no interactions, the rules of quantum mechanics don't stop applying. In fact, they get more noticeable when everything else is gone. Because quantum mechanics doesn't need much to operate. Just uncertainty, just possibility. And in a universe this empty, possibility is the only thing left. Let's break that down. In quantum physics, empty space isn't really empty. It's a seething field of temporary fluctuations. Even in a perfect vacuum, particles can appear and disappear, for no reason, just because probability allows it. Normally, these are tiny events. A pair of virtual particles might pop into existence and vanish a split second later. We don't notice because they're short-lived and because there's so much other stuff going on. But in a far future universe, where everything else is still, these tiny blips are all that's left. And the strangest part? Some of them might not be so tiny. In theory, if you wait long enough, quantum fluctuations could create almost anything. A single particle, a molecule, a full atom, even an entire brain. Yes, a brain. That's not a metaphor. Physicists have seriously considered the idea that in the vast, empty future of the universe, it's statistically possible for a fully formed, conscious brain, complete with thoughts, memories, and sensations, to appear out of nowhere. No body, no planet, no galaxy, just a lone, disembodied mind. This is called the Boltzmann brain problem. It's a thought experiment named after Ludwig Boltzmann, a 19th century physicist who developed ideas in statistical mechanics and entropy. He suggested that order can spontaneously emerge from disorder if you wait long enough. Not often, not predictably, but sometimes. Now take that idea and stretch it. In an eternal quiet universe, with quantum fluctuations forever bubbling in the background, the odds of weird things happening don't go to zero. They just get smaller. But with infinite time, even small odds eventually pay off. So imagine a brain pops into existence. Maybe for a second. Maybe with a memory of a life it never lived. Then it dissolves again. It sounds absurd. And it is. But it's a real consequence of how quantum mechanics works in an old, quiet universe. Now think bigger. If a brain can appear, what about a whole planet, or even a new universe? Quantum tunneling doesn't just apply to particles. In theory, entire regions of space could tunnel into new states, like a fresh vacuum with different laws of physics. That new vacuum could expand into its own universe, completely disconnected from ours. So even in death, the universe isn't quite done. Not in the way we thought. It's not alive, but it's also not still. It becomes a statistical playground. Most of the time, nothing happens. But sometimes, just rarely enough to be strange, something flickers into being. A brain, a flash of light, a new set of physical laws, a universe rebooted from noise. And here's the real philosophical twist. If these fluctuations happen often enough, then the most likely form of consciousness might not be life that evolved naturally, but isolated moments that randomly appear. That's the Boltzmann brain paradox. If the far future produces more fake minds than evolved ones, then you are left with a momentary illusion. The point is, once matter is gone, and stars are dead, and black holes have vanished, and even particles have decayed, the universe doesn't go silent. It goes probabilistic. It starts dreaming in quantum blinks. No narrative, no purpose. Just statistical possibility acting out weird scenes in an otherwise empty void. And that brings us to an even bigger question. If nothing meaningful is happening, if all that's left is randomness, then does time still exist? So now the universe has reached a place that doesn't even look like a place. There's no structure, no activity, no direction. Just empty space stretched across distances too vast to describe, filled with the faintest traces of radiation and the rarest quantum flickers. The stage is still here, but the actors are long gone, the lights are off, the story, it seems, is finished. But one question still hangs in the dark. Is time still ticking? Ludwig Boltzmann and Sean Carroll are two leading scientists whose work underpins the ideas about the arrow of time, entropy, and the notion of time becoming frozen in a maximum entropy universe. It's easy to assume that time just keeps going. After all, it's baked into everything we do. One moment follows another. We age, things change. But in physics, time isn't an independent thing floating in the background. It's tied to change, to entropy, to memory, to difference. And in a universe where nothing is changing, it's fair to ask, what does time even mean? In our world, time has a direction. We call it the arrow of time. It points forward because entropy increases. Systems go from order to disorder. Ice melts, stars burn out. That's how we know time is moving. But when everything reaches maximum entropy, that arrow starts to wobble. Without new disorder to create, there's no sense of before and after. No reason to say this moment is different from the next. The universe doesn't rewind, but it also doesn't progress. It just floats. Think of a paused video. Technically, it's still running. The playhead is there, the frame is loaded, but nothing's moving. That's what time might feel like in the final state of the universe, not like a clock ticking, but like a frozen frame that never updates. Now here's where things go deeper. Even if some last flickers of quantum randomness still occur, like the occasional Boltzmann brane or vacuum fluctuation, those events don't build anything. They don't accumulate, they don't leave records, they're self-contained and gone in an instant. So even if time technically exists, there's no memory of it, no history, no information to mark one moment from the next. And without information, physics starts to lose its grip. Because physics is built on predicting change, on using what we know to figure out what's next. But if there's nothing to observe, nothing to measure, and nothing to remember, what's left to describe? Maybe this is where physics ends. Not with a singularity, not with a collapse, but with silence. Not just the absence of sound, but the absence of meaningful difference, a kind of stillness, where even the concept of stillness doesn't really apply because there's no contrast. It's a strange conclusion. The universe doesn't die, it just loses context. And that brings us to the other half of this final decay: information. Information in physics isn't just words or data, it's about state, configuration, knowing how something was arranged, a single particle's position and momentum, a black hole's mass and spin, a bit on a hard drive. It's all information. One of the biggest open questions in physics is whether that information is ever truly lost. For decades, scientists argued about black holes. When they evaporate, does the information about what fell in get destroyed? Or is it somehow preserved in the radiation they emit? Stephen Hawking thought it was lost. Later, he changed his mind. Others say it's encoded in subtle correlations. Some think it's written on the edges of space-time itself. But when the whole universe fades into cold radiation and statistical noise, the same question echoes louder. Is the information about our universe, about you, me, every star, every planet, still somewhere? Or has it all been erased? Maybe it's imprinted in the geometry of space. Maybe it leaked out during expansion. Maybe it's trapped in quantum entanglements we'll never untangle. Or maybe, over infinite time, it simply decays bit by bit, moment by moment, until the very concept of memory becomes meaningless. And if that happens, then time doesn't just stop moving, it stops existing. Because without memory, there is no before. Without difference, there is no after. And without both, there is no time. Just space. Cold, flat, quiet. Waiting for something that might never come. We follow the universe from light to dark, from stars to silence, from energy to entropy. Everything that could shine has dimmed, everything that could collapse has collapsed, and now even time itself barely has a role to play. But there's one idea that keeps coming back, quietly, subtly, persistently. Could it all start again? Not because of divine intervention, not because of a reset button, but because of physics. Because of the way our universe seems to behave at its most fundamental level. Let's rewind just for a moment to the earliest state, not the stars or the atoms, but before that. The Big Bang wasn't just an explosion of matter and energy, it was an explosion of space itself. And that space, according to modern cosmology, didn't appear out of nowhere. It might have been a patch of a much bigger structure. A bubble in an inflating multiverse. A region where energy dropped and space cooled, and laws of physics crystallized into what we now call our reality. That process is called cosmic inflation, a rapid expansion that smoothed everything out before the universe even had a chance to form particles. And here's the thing, inflation might not be over. Not everywhere. In some versions of the theory, inflation is eternal. This variant of the inflation theory, notably developed by Andrei Linde, Alexander Vilenkin, and others, proposes that inflation does not end uniformly across all of space. Instead, while some regions of space stop inflating, forming pocket universes like ours, other regions continue to inflate indefinitely. Space keeps expanding, bubbling off new regions, each with its own physics, its own constants, its own rules. Our universe might just be one tiny patch in a much bigger multiverse, one of countless other bubbles, each sealed off, each born in its own quantum fluctuation. So even if our universe goes cold, even if it ends in silence, it might just be a single dead leaf in a cosmic forest still sprouting new branches. Somewhere, out there in the larger inflating landscape, another universe might be starting right now, and not because ours ended, but because that's just what space does. It makes more space, over and over again. That's one kind of restart, external. But there's another possibility, an internal one. Quantum tunneling isn't just a trick for particles, it's part of the universe's fabric. Even in a totally flat, low-energy space, there's still the chance that a new fluctuation could cause a local region to pop into a different vacuum state, a different configuration of fields. That's not just a weird patch. That could be a new universe. If that new bubble is stable and if it grows fast enough, it might pull away from our dying universe and become its own self-contained reality. Different physics, different time, a new beginning from old quantum noise. And here's where it gets strange. There's no clear reason this couldn't happen more than once. Over trillions of years, more and more of these bubbles might appear. Most will collapse immediately. Some might not. A few might stabilize. And maybe, every once in a while, one of them finds just the right conditions, just the right vacuum energy, just the right symmetries, and becomes something like what we'd recognize as a universe. In that sense, the end of our universe isn't a wall, it's a branching point. The rules we know don't stop, they just fork and detour, and that brings up a big question. Could this have already happened before? Maybe the universe we live in now isn't the first. Maybe it's one of many that have flared up, expanded, cooled, and gone quiet. Maybe this cycle has happened an infinite number of times, in infinite configurations. There's no observational evidence for this. But there are hints. The prior state before the Big Bang, the fine-tuned nature of our physical constants, the odd coincidences in how inflation worked, the way black holes, entropy, and quantum fields seem to know more than they should. We don't know for sure, but it's not impossible to imagine a system where universes rise and fall, not by design, but by statistics. Where creation isn't a singular event, but a natural process. And where the thing we call nothing is really just the background waiting to be something again. So even in the quietest, coldest possible version of existence, there's a crack in the silence. It doesn't promise anything. It doesn't guarantee a rebirth, but it leaves room for one. And maybe that's enough. After all that, after black holes and proton decay, quantum blips and vacuum bubbles, the death of time and the quiet drift of radiation, you'd think the weirdest part of physics would be out there, buried in the math, in equations, in entropy, in the ghostly rules that hold everything together. But it's not. The weirdest part is us. Think about it. We're small, ridiculously small. A human being is barely a shadow on a rock orbiting a star in a galaxy among billions. Our lifespan doesn't even register next to cosmic time. We are made of atoms that barely stick together, animated by electrical signals and chemicals, all operating for a blink of time and then gone. And yet, we noticed. Somehow, the universe got old enough, quiet enough, structured enough to make minds. To create something that could look back at all this and try to understand it, to ask questions, to trace the history of stars and imagine the future of space, to write stories about the end of time. That might be the strangest twist in all of physics. Not that the universe ends, not that time dies, but that before all that happens, somewhere along the way, a species evolved that could care. We're not built to grasp cosmic scales. Our brains evolved to spot patterns in trees and react to rustling in the grass. But here we are, staring down trillion-year futures, talking about vacuum decay, wondering whether time can end, whether the universe can reboot itself, whether anything we do really matters in the long term. And maybe that's the point. Not in the sense of a plan or a reason, but in the sense that we are part of the physics, part of the entropy, part of the brief moment when matter organizes itself into a structure complex enough to ask, what's next? We don't know how long we'll last, maybe not long at all. Civilizations are fragile, planets are temporary, stars burn out, but for this one moment, we're here. Alive during the light, thinking about the dark. And that makes us, in some sense, witnesses to the story. Who invited us to this cosmic gathering? But we showed up anyway. And we turned our eyes toward the sky and tried to figure out how the story ends. And maybe that's the closest thing to meaning we'll ever get. Not that the universe lasts forever, not that something comes after, but that something inside it tried to understand it, before it was too late.